All right, hey there, Math 2150. So you're coming to the last section that we're going to test in this chapter. So 3.4 is the last part of this chapter. So just FYI, the test will be on sections 3.1 through 3.4. And the good news is that 3.4 is kind of a break from that long process that you were accomplishing in 3.3. Okay, so to get started, section 3.4 talks about two principles, and I've already written one down on the screen. The first principle is called the max-min principle number 1. And the requirement to use max-min principle number 1, it has to have a closed interval, guys. So the equation, or not the equation, but the problem has to have a closed interval. Okay, and so I'll write an example like A to B. So it has to be on a closed interval. So I've drawn this picture over here to the left, and right now it's not closed, right? So right now, this graph continues to go in both directions because I've drawn arrows on it, okay? So continuous function that just continues to go on and on and on forever. But I can close this interval, and that's exactly what I'm going to do. So let me see here. Yeah, we'll go like that. So let's say I close this interval from -4. No, let's go -3. Let's go -3 to +3. So now we're only looking at the graph from -3 to +3. Okay, so literally if I come up here, I'm only looking at the graph from -3 right here to +3. Okay, so I'm trying to explain this principle to you. So if I highlight, I'm looking at this part of the graph right here, this part only. And so guys, if you take a look, we have what we call an absolute min and an absolute max. An absolute min and an absolute max is the tallest of the tall or the lowest of the low, okay? So the absolute max is the top point, and the absolute min is the bottom point. So take a look. In this example, the tallest point clearly is right here. So your absolute max is happening at -2, 1. And if we take a look, your absolute min is happening right here. And so right there, absolute min would be -2. No, excuse me, that's +2, +2. Okay, so the absolute min and absolute max, there it is. Okay, but now let me draw this other picture for you. Okay. So I've got this other cubic, okay, and let's say okay, so now let's say I want to look from, I don't know, -3. Let's go, I want to look from -3 again to +5. Okay, so now I'm looking over the interval -3 to +5. So if I go up here and close off my interval, -3 is right here. Okay, and +5 is right here. So if I highlight the graph that I'm looking at again, I'm looking from here to here. Okay, so if I take a look, I'm going to start with what I think is the most obvious. I think we all will agree that this point right here is the lowest of the low. So we'll assume that point is that's +3, -1. So +3, -1 is my absolute minimum. It's the smallest or the lowest point on the graph. But take a look now. Some of you may come over here because you automatically think that's the max, and you're not wrong. It is a maximum, but it's not the absolute max. The absolute max, again, is the tallest point on the graph, and the tallest point on the graph, guys, is actually over here where I'm drawing a mark. Okay, so that point right here, let's say that's 1, 2, 3, 4, 5. So we'll say that is +5, +5 is my absolute max. Okay, so if you take a look, let me make this bigger. If you take a look, guys, that's what we've got going on. So what you've learned here is the absolute maxes can happen and absolute mins can happen at the max and the min typically. So right here, this is a normal min and a normal max and a normal min. But on the second example, you saw that the absolute max and min happened at an endpoint, okay? And so max min principle number 1 says that your absolute min or your absolute max might happen at critical values because, again, guys, critical values from back in section 3.1 we learned is where maxes and mins typically happen. So it can happen at critical values or it can happen at endpoints, okay? So if I look at an example, and I'm actually pulling this example from the PowerPoint. So give me 2 seconds to pull it right back up. So the function that we're going to look at is, hold on, right here. We're going to look at this function. So here's an example problem using max-min principle number 1. So we have f of x equals x cubed minus 3x squared, minus 3x plus 2. Okay, and I want you to find the absolute maxes and not the absolute maxes, but the absolute max. And I want you to find the absolute min. And I only want you to look at the interval from 0 to 3. Okay, so we're only looking at the interval from 0 to 3. That's my closed interval. So again, maxes and mins can happen at critical values. And how do we find critical values? We take the first derivative and we set it equal to 0. So if we take the first derivative, we get 3x squared minus 3. Okay, that's derivative, the first derivative. So if I set 3x squared minus 3 equal to 0, I would add 3 and get 3x squared equals 3. I would divide by 3. I would get x squared equals 1. I would take the square root, and you better remember when you take a square root, you get a positive and you get a negative. So we have 2 critical values right here. Critical values for those of us that need all the notes. Okay? But here's the thing, guys. You're only looking at the interval up here. If I highlight it, you're only looking at the interval from 0 to 3. Well, your critical values was x equals 1 and x equals negative 1. But guys, negative 1 is not in this interval. So we are not going to test it because we don't care what's going on at negative 1 because the problem specifically asked for you to only look from 0 to 3. Okay? So in order to find the tallest value or lowest value, guys, tallest and lowest values are y values. And how do you find y values? You plug in your x values to find your y values. So we are going to find f of 1. We are going to find f of 0. And we're going to find f of 3. Okay? Why f of 1? Because 1 was a critical value. Why f of 0? Because 0 was an endpoint. Why f of 3? Because 3 was also a endpoint. And so here's f of x. So if I go back and plug in, it will be 1 cubed minus 3 times 1 plus 2. So that is 1 minus 3 plus 2, which is 0. So at 1, we have a height of 0. Now we go again. Now we plug in 0. So it'll be 0 cubed minus 3 times 0 plus 2. Well, 0 cubed is 0, minus 0 is 0, plus 2. So we get a height of 2. So if we were only looking at these 2 values, guys, this 0 would be my minimum, my absolute minimum, and this 2 would be my maximum because 0 is smaller than 2. So we have a minimum and we have a maximum. But we're not done. We have to play with that third value. So we have to plug in 3. So it'll be 3 cubed minus 3 times 3 plus 2. So that's 27 minus 9 plus 2. 27 minus 9 is 18, and 18 plus 2 is 20, I think. And so clearly, guys, 320 is the tallest value, which means that is my absolute maximum. And 10 is the lowest, which means 10 is my absolute minimum. Okay, and so there's my absolute min and my absolute max, and that concludes 3.1 max min principle number 1. Okay, So now let's go look at max-min principle number 2. So max-min principle 2. Okay. Like up here, the requirement for max-min principle number 1, it had to be a closed interval. In order to use max-min principle number 2, the requirement or the circumstance is that there has to be only one critical value. Okay, that is the requirement. Okay, so I think I'm just going to jump into using max-min principle number 2. Well, actually, let me give you a little bit more notes. So max-min principle number 2 says the f of c, so the critical value's height, okay, is an absolute max if the second derivative, okay, the second derivative of that critical value is less than 0. And it also says f of c is an absolute min if the second derivative again at c is greater than 0. And you may say, what the heck is this meaning? Well, if you learned what you were supposed to learn in the last section in 3.2, if the second derivative is less than 0, that means the second derivative is negative, guys. And if the second derivative is negative, I hope you remember second derivative negative means concave down. And concave down looks like this. And clearly, guys, if your graph looks like this, you're going to have a maximum. And that's exactly what it says. There's going to be a maximum. Vice versa on this second one right here. If your second derivative is greater than 0, that means it is positive. And if the second derivative is positive, that means you are concave up. And concave up looks something like this. So if it looks something like that, you can clearly see it is a minimum. Okay? So that is how we use max-min principle number 2. So let me give you an example of this principle. So we're going to look at, this is also an example. This is example 3 from your PowerPoint. So if you want to take a look at it on there too, sometimes it just helps to hear it. So we have f of x equals 4x minus x squared. And the question wants you to find the absolute max and min. And it does not give you an interval, okay? So guys, there is no interval given in example 3. And so because there's no interval given in example 3, you automatically know that you're not going to use max-min principle number 1. So we're going to attempt to use max-min principle number 2. And when we use max-min principle number 2, like it said, we hope that there's only one critical value. So let's find the critical value. How do we find critical values? We take the first derivative. The first derivative will be 4 minus 2x. And then we take the first derivative and set it equal to 0. If we subtract 4 on both sides, we get negative 2x equals negative 4. Let me roll up a little bit, guys. Divide by negative 2, divide by negative 2. We clearly get x equals positive 2. So, woohoo, this is good news. We only have one critical value, which means we can go attempt to use max-min principle number 2. And again, what does max-min principle number 2 say? It says to take the critical value, this right here is your critical value, and plug it into the second derivative, okay? Well, we don't have the second derivative. So by golly, we got to go find the second derivative. So the second derivative, the first derivative was 4 minus 2x. So the derivative of that, the derivative of 4 is nothing. And the derivative of negative 2x is negative 2. Okay, so there's the second derivative. So we need to plug in our critical value. So we need to take the second derivative and plug in 2. And so negative 2, guys, there's nowhere to plug x in. So the answer is clearly just negative 2. And I don't care that the answer is negative 2. Similar to earlier sections, I just care that it is negative. And if the second derivative is negative, that means, just like up here it says, that means that you are concave down. And for those of us that still need a picture, concave down looks like a frown. And so if you're concave down, you are clearly going to be a maximum, which means x equals 2 is a maximum. And it's not just a maximum, it's the absolute maximum because it's the only one on the graph. It's the absolute max. So if it's the absolute max, again, guys, a max is not an x value. A maximum is an ordered pair, is a point, which means we need an x and we need a y. So now we need to go back and get our y value. So if I plug 2 into the original to find my y value, 4 times 2 minus 2 squared, roll up a little bit more, that is 8 minus 4, which equals 4. And so the actual ordered pair, gang, is 2, 4. So what did you just show me? That 2, 4 is your absolute max. And you may say, well, what about the absolute min, Miss Floyd? Well, there is no absolute min because there was no critical value. There's only one critical value, which means there's only one possible max for min. And we didn't close the interval, which means maxes and mins can't happen on a if the interval's not closed, okay? So there is an example of max-min principle number 2, okay? So again, the requirements are to use max-min principle number 1, you have to have a closed interval, and to use max-min principle number 2, you have to have only one critical value, okay? And the problems are designed for these circumstances to happen.